Hi guys, welcome back to our YouTube channel. So today we are learning about stability in control systems. What is even stability? Stability in control system refers to the ability of the system to return back to its steady state after being disturbed. You can also drop your ideas on stability in the comment section. So moving on. As a control system is stable if for every bounded input, the output also remains bounded. So consider an automated blood pressure control system used in an intensive care unit to adjust the medication delivery. So this is how it works. The sensor measures the patient's blood pressure, whilst the controller compares the measured blood pressure to the target level. The actuator delivers the medicine to rise or lower the blood pressure. So this is what a stability looks like. So if the patient's blood pressure suddenly rises, the monitor will detect the increase in the blood pressure and the system will reduce or stop the medication. Then the blood pressure will return back to its normal range. This is what stability is basically all about.
In control systems, we have several important types of stability. We have the absolute stability, which refers to the stability of nonlinear systems using specific criteria. This determines if the system is stable for all possible inputs within the range. We also have marginal stability. Marginal stability, the system neither grows nor decays, but continues oscillating. In this, the output remains bounded but does not settle to zero. Example is the pure sinusoidal oscillation.
This is another type for stability and is unstable system. For unstable system, its output increases without bounded over time. Even a small disturbance leads to large deviation. For example, for unstable system is exponential growth response. And another type for stability is relatively stability. This also measures how stable a system is. It also indicates how fast the system returns to its equilibrium. Often, it analyzes use damping ratio poles locations in a complex plane.
How to determine the stability of a system. The key idea here for stability is that a system that is stable has its output bounded for any bounded inputs. So the key criteria to determine the stability of a system is to focus on its closed transfer function, the poles of the closed transfer function. So for any given stable system, the poles lies on the left side of the S-plane and vice versa for an unstable system. That the poles will lie on the right side of the S-plane. And for a marginally stable system, its poles lie on the imaginary axis.
The necessary condition needed for a system to be stable is that the characteristic equation must be positive and then a non-zero. To fully check for stability, we use the Hurwitz criterion by forming a Routh table. If all the elements in the first column are positive, the system is stable. But if the sign changes, the system is unstable.
So the Hurwitz criterion states that the number of roots of a polynomial that lies on the right side plane is what? Equal to the number of changes in the first column. So if a system has poles on its right side, the system is what? Said to be unstable. The Hurwitz criterion is an essential tool for analyzing control system stability. But what happens when the standard math breaks down? That is where the special configurations come in. These special cases are four. So we'll be moved on to the first one. So the first one is a normal standard configuration. No element in the first column is zero. You simply complete the array and count any sign changes to find your unstable roots. Straightforward. And then for case 2 occurs when you hit a single zero in the first column. While the rest of the row contains non-zero elements, the workaround, replace that zero with a small positive constant, that is epsilon. You complete your array, then evaluate the signs at epsilon, which approaches zero. So case 3. For case 3, which is known as what? The all zero row. This indicates roots located symmetrically about the origin. To bypass this, look at the row directly above to form an auxiliary equation. Take its derivative with respect to s and use those new coefficients to replace the 0 and continue. And then for case 4, which is presented exactly like case 3, but specifically involves repeated roots on the imaginary omega axis, j omega axis, sorry. When this happens, regardless of the rest of the table, the system is inherently unstable. So mastering these 4 cases ensures that no root table will store your analysis. Thank you.
In the question given, we are expected to find and check the stability of our system given the characteristic equation. So we'll be given this equation and then we're asked to check for its stability. So first of all, we are going to check whether this equation we have, which is a polynomial, is a Hurwitz polynomial. So for a polynomial to fall under a Hurwitz polynomial, all the coefficients of the powers of s should be positive and non-zero. Looking at this equation, all the coefficients of various powers of s have values and then they're all positive. So which means that this polynomial falls under a Harris polynomial. By checking for stability, this is not enough. So we move on to using the Routh criterion and then we then develop our Roussian array. Developing our Roussian array, we use the coefficients of the powers of s, and that's 1, 2, 3, 4, and then 5. So these are our coefficients. We draw our Roussian array. So in this side, we write the various powers of s, and that's starting from s power 4, which is the highest, s power 3, s power 2, s, and then s power 0. So in filling the first two, so a simpler way to fill the first two is that looking at the coefficients, we take the first two and then we start with 1, then move with 2 in the next row, and then we continue with 3, 4, 5, and then there's nothing, so we can just write 0. To calculate the remaining rows, that's for the rest of the powers of s, we'll be using the root array determinant. And then for that, we'll take this first column, that's for the first element over here for the s square value. We'll take the first column and then we'll use it with this and then perform the determinant, the root array determinant method on it. And then for the second value, we'll take this first column, the same first column, and then we'll take it with this one. So if there were other values, we'll take the first column and then with the next, and then we did that way. So for this, let's take that element as B1. So to calculate for B1, we'll take this and then this. So we'll use the values of 1, 2, and then 3, 4. So calculating this, we take this multiplied by this, and then we subtract it from this multiplied by this. Then we divide by the value over here. So when we do that, we get 2 multiplied by 3 minus 1 multiplied by 4. Then we divide by 2. Working out, we have a value of 6, and then we get a value of 1. So the value over here would be 1. And then for the next element, we still take the same first column and then the values of them 5 and then 0. So let's take that to be B2. So calculating B2 would be using 1, 2, and then 5, 0. Using the same way we calculated this one, we'd have 2 multiplied by 5 minus 1 multiplied by 0 divided by 2. And then we have 10 over 2, giving us a value of 5. Meaning the value of this second element will be 5. And then we don't have any other value here, so we're done with the second, the coefficient of 2, the row for that one. And then we would then have the row of s power 2 to be 1 and then 5.
So moving on with the filling of our table values for S1 and S0. For S1, we use the values in the two rows right above it. That's 2, 4, 1, and 5. So this will be used as our matrix. And then to find the value for the first column of the S1 row, it would be 1 times 4 minus 2 times 5 all over the value right here 1, which would be 4 minus 10, which is minus 6. So that's what comes here. But since we don't have any values here to fill the table, here becomes 0. So we are done with the first S1 row. Then we move on to the S0 row. To find the S0 row, we take the two rows right above it. That's 1, 0, minus 6, and then 5. So those will be the values of our matrix, which would be 1, 5, minus 6, and 0. So we do the same thing we did for the S1 column, which would be minus 6 times 5 minus 1 times 0 all over the value just here, which is minus 6. And this would be minus 6 times 5 all on minus 6, which gives us 5. So this 5 will be the value here, and that ends it for the table. So the next thing we have to do is to interpret our table we've gotten. And so to interpret it, we need the values in our R1 column, which is 1, 2, minus 6, and 5. Number of sign changes between the values. So when we look at the R1 values, we see that from 1 to 2, there is no sign change. They are both positive. Same as from 2 to 1, they are also positive. But from the S2 row and S1 row, notice that there's a sign change, which is positive 1 to minus 6. And then from the S1 to S0, we notice that there's also a sign change, minus 6 to 5. That gives us two sign changes. And so from our Hurwitz criterion, we know that these values tell us how the roots of the equation are going to look like on the real number line. So having two sign changes just tells us that there are two roots that are on the right hand side of our graph when we map it out. And so that tells us our system is unstable. If we had one sign change, it will still be unstable. But if we had, for example, a 0 in our R1 column, that tells us that it's marginally stable because there will be the possibility of one root being on our j omega axis. But if there are no sign changes, then it tells us our system is very stable because they will all be on the left hand side of our graph.
So in this example, there are two sign changes, so the system is unstable.
To understand what this means in a real-time world context, let's consider a biomedical application such as an infusion pump. In such a system, the output represents the drug delivery rate. Because the system is unstable, even a small disturbance or error in the input would cause the output to increase uncontrollably over time instead of settling at a desired value. This could lead to excessive drug delivery, resulting in overdosing and posing serious risks to the patient. Therefore, the system is not safe for practical implementation unless it is redesigned or stabilized.
Thank you for watching our video. Please like, comment, and share.